Hello everybody and welcome to chapter number 6 in statics. My name is Professor Algara and I will be talking today about a lot of content related to structural analysis. This chapter, it's another one of the shortest ones, so I hope this video won't be that long. I will be solving a few exercises and then after that I will just be open for questions through the email. So a truss is a structure composed of slender members joined together at their endpoints. If a truss along with the imposed load lies on a single plane, then it is called a planar truss. A simple truss is a planar truss which begins with a triangular element that can be expanded by adding two members and a joint. For those trusses, the number of members and number of joints are related by the following equation, and this is only for design purposes, and you will learn later on how we can use that. But ultimately a truss will be a combination of different elements that will be carrying loads, and then our job will be to study those members. So analysis and design assumptions, and this is very important, and that's actually one of the things with this chapter. It has a lot of information about theory. So when designing the members and joints of the truss, first it's necessary to determine the forces in each truss member. This is called the force analysis of a truss. When doing this, two assumptions are made. All loads are applied to the joints. The weight of the truss members is often neglected, as the weight is usually small in compared to the forces supported by the members. The members are joined together by smooth pins, and these assumptions is satisfied in most practical cases where the joints are formed by bolting the ends together. So at the end of the day, you will have a bunch of members that are connected together, and they are connected through pins. What we do, we study those pins. As we study each one of the members will be subjected to different loads, and those loads could be in loads in tension or loads in compression, as you can see right here. Usually compressive members are made thicker to prevent bulking, but that's not part of statics right now, but you will have it in material science. So there are different methods to study these type of structures. So the first one is called the method of joints, and when using the method of joints to solve the forces in truss members, the equilibrium of a pin is considered. All forces acting at the joint are shown in a free body diagram. This includes all external forces, including support reactions, as well as the forces acting in the members. As you know, equations of equilibrium in X and Y are used to solve the unknowns. So what it's very important right here, as you have the truss, what we actually do is to study the pins in which all the members are joined together. So AB goes to this pin right here, BC also goes to that pin, and then you have the force acting on it. And that's why studying those pins is what will give us the information that we need to design the trusses. And after that we need to apply the equations of equilibrium, which is sum of forces in the X direction, Y direction, and the moment, the ones that we know. So steps for analysis. This is a step that is being laid out in the book, but as you solve more and more exercises, you will start getting your own methods, but let's just stick to this one. If the truss supports reactions are not given, draw a free body diagram on the entire truss to basically get the support reactions. And usually to solve that, we need to use the equations of equilibrium with the whole truss. Then after that, we need to draw the free body diagram of the joint with one or two unknowns. And usually we will assume all the time that the forces are going in tension, and obviously if we get a negative value, then that will mean that it was not in tension, it was actually in compression. Okay, but that's very important. We just take the pin and we see all the forces that are related to that pin. So number 3, we need to apply the equations of equilibrium to that pin. Sum of X forces in the X direction equals 0, as well as sum of forces in the Y direction, so we can find the unknowns. Then we need to repeat step 2 and 3 to each joint in succession until the required force are calculated. So if a joint, and this is very important because this will simplify your calculations by a lot. So sometimes you will have a trust with different members, right? If you can find the zero force members, then you will be saving yourself a lot of time. So if a joint has only two collinear members and these are not external loads, and there is no external loads or support reactions at the joint, then these two members are zero force members. In this example, members DE, DC, AF, and AB are zero force members. You can easily prove these results by applying the equations of equilibriums at joint D and A. Zero force member can be removed, and then we can analyze the truss with the ones that are not zero. So this is a lot of theory, like I said. All of this, it's a lot of information. But if we focus on point A, for example, if you take a look at that point A, if we do a free body diagram, we will have intention, that's what we assume, and this is A, I'm just gonna label, so this is F, AF, and then we have another force right here that we will call FAB. If you do sum of forces in the x direction equals 0, the only force that we have right here is FAB. So therefore, that force is not doing anything to your system. If I do sum of forces in the y direction, you will find that it's exactly the same thing. The only force acting in the y direction at pin, because remember, we're studying the pins. At pin A, it's FAF. So something very important that I need to clarify, and that even though they don't carry any force, right, and they're called zero members, they're usually added for stability to your system. Okay, then that will make the system more robust, and maybe because of that it will make the system more stable. But when you are actually looking for the reactions, you can remove those members and then have a simpler truss like this one, in which you will have less nodes involved and obviously less reactions. So like I said, the zero force member, when they're removed, that particular thing will simplify your calculations. So here we have another example on how you can start simplifying your system from here to here. Okay, and I just don't want to go over the whole reading because it's basically repeating the same thing. If we study pin D or pin C, if you do sum of forces at those pins, you will realize that the forces are equal to 0, and therefore they will become zero force member. And because of that, you can easily remove them for studying purposes. Okay, they were added to add more stability, but at the end of the day, you can remove them in order to do your calculations. Okay, and it's basically the same thing that we just talked about in the previous slide. But just like I said, it's always easier when you have everything given with an example, and I think that will help you more. But let's just see. So you have the system right here, as you can see, and we need to find the forces in each member of the truss. Okay, so what should we do? We should check first if there's any zero force member, and then after that we should analyze pin A and then pin A, and then that's it. And if we go with that plan, everything should be fine. So something very important to realize here is that the force BD, or the member BD, it's a zero force member. How do you know that? So if you go right here at B, and then you apply your free body diagram, you have FBD, and then you have two forces going as tension. If you do sum of forces in the y direction, you will realize that FBD it's equals to 0, and therefore you can remove that element to simplify your calculations. Okay, and then you will realize that FDD it's a a zero member, and that will help you perform the calculations. How so? So after that, I will go to pin D, and the reason why I'm going to pin D is because where I have the most unknowns. I have FAD and FCD, and remember, you're always assuming that goes in tension, but then I got rid of the one that's supposed to be in the middle, because that force, which is BD, I already knew that it's zero. So that's how you simplify that, by removing the zero, the zero members, the zero force members. So now what we have to do at point D is very simple. So now all we have to do is to apply the equations of equilibrium. So sum of forces in the x direction, always, put your sign convention, will be equals to minus 450, which is this guy right here, and then we have plus FD, actually FCD, that has been multiplied by the cosine of 45. And then I have also minus FAD, that also multiplies to the cosine of 45, and that's equals to 0. Therefore, my first equation, now I go with the second one, which is sum of forces in the y direction, positive going up, and that will be equals to minus FCD going down, obviously, that multiplies sine of 45, and then I also have minus FAD, that is multiplied by the sine of 45, and then this is equals to 0, and that will be my second equation. Something very important, where did I get the 45 degrees? Super simple. If you have a triangle right here, and this triangle has 4 and 4 equal, each one of its sides are equal in measurement, that means that you have a 45-degree angle. Don't forget that. So when I solve the equation, solving the equations, I will get that FCD it's equals to 318 pounds, and FAD it's equals to minus 318 pounds. So that will bring me to a very important topic. You have two options right now. You can either flip the direction of force AD, or you can just keep moving forward with your calculations by plugging minus 318 in all of the equations. So if at first you assume that everything was tension, it doesn't matter, because now you got a negative value. If you place the same negative value into the following equations, then you don't need to flip the direction of the arrow. But if you want to do it the other way, that's also okay with me. Okay, I just wanted to tell you what it means when you get that negative value. As far as me goes, I always keep the same sign convention. I don't flip anything. I just keep including the negative value in those equations. So now if I wanna go and analyze A, so after I got all the calculations and I got my FAD, I just only need to analyze point A in order to find what I need, and we already know the value of this one, and that one is obviously a negative value. So if I analyze point A, and then I go with the sum of forces in the x direction equals 0, I will realize that FAB it's positive plus, and then this is the value that I will put in a negative way, that multiplies the cosine of 45, and I know that this one is equals to 0. Therefore FAB will be equals to 225. Okay, and once I have that value, I will be concluding the exercise. The real question would be, do I really need to do pin C? So that will move us to our second method right now, which is the method of sections. And this is very, but very useful, especially when you have a system that has so many elements, okay? So in the method of section, truss is divided in two parts, right? By taking an imaginary cut through the truss. Since truss members are subjected only to tensile or compressive forces along their length, the internal forces at the cut members also will be either tensile or compressive, with the same magnitudes as the forces at the joint. You know, this result is based on the equilibrium principle and Newton's third law. Action and reaction, don't forget that, okay? So basically, if you have a member and you break the member into half, you can break it into two parts, but don't forget the internal reaction that will be created, you know, because of that cut that you place. And that could be compression or tension. So steps for analysis is very, very, very simple, okay? So at first you need to design how you need to cut the truss. This is based on A, where you need to calculate the forces, B, where the total number of unknowns does not exceed 3, because in general, you know, in these calculations you always have 3 equations of equilibriums up to now, so that's why you shouldn't be counting in any place that you will get more than 3. Then you need to decide which side of the truss will be easier to work with, and these right here I will tell you to go with the one that has less members because it's easier to calculate. So you can be lazy, I don't mind, because at the end of the day you will just get the same values as somebody that goes through the hard way. If required, you need to basically calculate the necessary support reactions by drawing a free body diagram in the entire truss and then apply equations of equilibrium. So what I'm trying to tell you is that if you think that you need to calculate reactions in these points, you know, before doing anything, you should calculate those reactions by applying the equations of equilibrium at the whole truss, and then you can break it out. Like I said, first of all, you need to decide where you want to break it. In this case was right here, and then you have 2 places or 2 results, this one and that one. Just go with the one that is easier to deal with, you know, the one that has less unknowns. Draw the free body diagram on the selected part of the truss, you know, it was either left or right, and then you need to indicate the unknown forces at the cut members. Initially you might assume that all members are in tension, you know, that's what I said, and you are using the same thing as you use it for method of joint, which is the one that we just described. Upon solving the equations, if your answer is positive, the member is in tension as you assume at the beginning. If it's negative, then the member is in compression. It's just as simple as that. You don't have to get, you know, things complicated. Then after that, just apply the equations of equilibrium and solve your system, okay? Usually you should have 3 by 3, but if I'm honest with you, when I had this class in my engineering school, it could go as long as 9 by 9 or 10 by 10, and I would have spent like 3 hours just going through these, solving the equations. All right, so now let's have an example, as always. All right, you have the following truss, and we've been asked to calculate the forces at KJ, KD, and CD. It says, well, the plan given by the book is that we need to cut, we need to work on the left side, and we need to calculate the reactions at A, and what are they, and then apply equilibrium of equations to find the forces. So this is a lot of, you know, blah 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 involved, but there's no simple path that they're telling us to follow. But now here I come with my analysis. So hear me out. So you have the truss, right? And you've been asked to calculate the forces right here, and then right here. Because of that, that's where you're going to make the cut. You're going to make your cut on a line that goes through those elements. Boom. That's the reason why. You will not make the cut right here. Why? I mean, you're not going to get anything that you need, so you have to do it through the members that are related to the unknowns that the problem is asking you to do. Once you have that, you will have two pieces. You will have this piece and you will have two pieces. Which one should you work? Right here it says like work with the left piece. Why? Well, it's very simple. You have less members involved, less forces, and if I look at it, you only need to do a simple sum of forces in order to get support reactions. Then you need to do a sum of moment, and to me it seems like it's going to be easy. Let's see. Well, like I said, you will break it up right there, and then you have to realize that you will get something like this. If you have something like that, where should I do moment? What do I need? So if I look at the problem right here, I will always go and do moment around the pin that will get me rid of the most unknowns. So for example, if I go with K, then these two things will not make any moment, and therefore I only need to focus on this one. But don't forget that the reaction at A was not given. Okay, sorry about this, it shouldn't be here. Forget about this, and we're gonna call that AY. Alright, so if I look at it, I just realized that I only have that unknown. If I go with this, then I have these two guys. So my gut is telling me that I should go with K. Which one you want to go for, it doesn't matter, because at the end of the day you will get the same results. But me, the professor, will decided to go with K. I know, and I knew that I will need the value of the reactions of A. But the theory told me that the first thing I should know is how to calculate the reactions before I break the trust. So this one right here only have G, Y. So if I were you, I will just pin G and I will do sum of moment around G. So sum of moment around G. Don't forget your sign convention in order to get the reactions at A. Why? Because there's no reactions in the Y, in the X direction on this pin, because it's a roller. Therefore, I only have Y. So if I do sum of moment at G, I know that the only force doing moment will be AY. Okay, so this is equal to 0. If I do that, then I will get that AY, and let's see if it's positive or negative. By using the right hand rule, AY will be doing a clockwise moment, which means that goes negative, and that will be AY. That multiplies the distance, and the distance is 2, 4, 6, 8, 10, and 12. That multiplies 12. Then I have 20 kilonewtons, which will make a positive moment. 20 kilonewtons. That's supposed to be multiplied by 10, which is the distance, and then I have a positive moment created by the 30 kilonewtons multiplied by 8, and then I have 40 kilonewtons that's multiplied by the distance, which is 6, because remember, I'm going around G. That's it's equal to 0, and therefore I get that AY will be equals to 56.7 kilonewtons, and that's how you get that value. Alright, if you do a sum of forces in the X direction, you will realize that the only force involved right here would be AX, and that's equal to 0. So AX is 0. Alright, my system seems to be very simplified, and now I only get to work with this because that's where I made the cut. So I got my reaction, I got the forces. So now the question, like I said, where do I do moment? The book will tell you to do moment maybe at C. It doesn't matter to me. So for me, I will make moment at K, because I feel like it will get rid of these two because they don't make any moment, and therefore the only unknown involved with this will be FCD. And if I do that, I will get sum of moment around K being positive in this direction. Then if I go with that, I will get right here, this is equal to 0, and I get minus 56.7. Remember, if you do the right hand, 56.7 is going clockwise, therefore is negative. That multiplies the distance, which is 4. and then plus the 20 kilonewtons, which is this, that is been multiplied by 2 as well. No, wait a minute. Yeah, by 2. And then I also have force CD, that has been, the distance will be from the force to the top, which is 3. Okay, so if I do that, this is equals to 0. I will realize that FCD, it's equals to 62.5 kilonewtons. Okay, now I got this one. So you have to realize that if you have this one already and this one already, I only have to do sum of forces in the X and the Y direction in order to get everything. So let's do that then. Sum of forces in the Y direction will be equals to 0, and I have 56.7 minus 20 minus 30 minus F KD, which is, we're gonna go with the component of this force, you know, this composed to this. I have the two sides of the triangle, so I can multiply this by 3 divided by the hypotenuse, which is 13. You know, if you go this one to the square plus this one to the square root of that, that's the hypotenuse of the triangle. So that it's equals to 0, and then if I keep solving for FKD, I will get that this is equals to 8.05 kilonewtons. I got this one, so the only one that I need to get will be FKJ, and I can simply do a sum of forces in the X direction equals 0. Don't forget your sign. Please don't forget that, because I will, you know, grade your exams based on that. So if I go with the sum of forces in the X direction equals 0, the only forces that I have, it's FCD plus FKJ plus the component of KD multiplied by 2 square root of 13, and this is equals to 0. This guy right here, it's been solved at 62.5, and then I also have this guy, which is 8.05. So if we solve for FKJ, we will get that FKJ was equals to minus 66.7 kilonewtons. Like I said, you can leave it as this, or you can just tell me that it's also equals to 66.7 being in compression. So don't forget your units, and that will be fine with me as well. If you want to leave it with a negative sign, I will be able to read that, but if you want to just let me know that that member was in compression, that's also good. Okay, I hope that was simpler. If you have more questions, I can go over this exercise with you one-on-one. All right, and finally we're getting into the end of the chapter, which is frame and machines. So frames and machines are two common types of structure that have at least one multi-force member. Frames are generally stationary and support external loads. Machines contain moving parts that are designed to alter the effect of the force. So a frame will look like this, a machine will look like this, and we'll be focusing on how to solve these type of exercises as you will have them in the book. These are a little bit more complicated. I mean, these ones are complicated, but these ones are also complicated, okay? Because of that, there is a few steps for analyzing a frame or a machine, and it works for both of them. So at first, you know, we need to draw a free body diagram of the frame or machine and its members as necessary, as you know, very simple. A few hints: we need to identify if we have two force members. Know that forces on contacting surfaces, usually between a pin and member, are equal and opposite, and For a joint with more than two members or external forces, it is advisable to draw free body diagram on the pin. So when you have a system like this one, if you want to break it up into two parts, the same rules will apply as we've been discussing. You can break it up, no problem, but don't forget the forces, internal forces that are related to it. That's the most important thing with this. And if you want to get rid of the supports as it was taught throughout your chapter, don't forget to add the reactions that are connected to that. Then we need to develop a strategy to apply the equations of equilibrium to solve for the unknowns, and then that's it. You know, problems are going to be challenging since there are usually several unknowns. A lot of practice is needed to develop good strategies and ease of solving these problems. Guys, these problems will require a lot of concentration on your end. You can have a system that has, you know, I don't know, maybe 20 elements, and if you have 20 elements and you don't apply the theory as you should, you know, using all of the methods that I've just explained it to you, you can spend hours in solving these exercises. Like I said, it happened to me when I had this class in engineering school. So I'm just gonna go ahead and show you, because I'm not going to be solving this problem. I'm just going to show you, you know, the strategy that the book used. And the reason why I'm not going to be solving this is because I want you to pay attention as much as possible so you can realize the analytical steps that they basically did follow. So you have a whole system right here, and the whole, you know, the wall crane supports an external load of 700. That's your first hint. So we need to calculate the force in the cable and also the horizontal and vertical components of pin reactions at A, B, C, and D. So A, B, C, and D. So this is the way I see it. You have to break up this problem in a way that you have a clear path on how to solve it. If you start with the reactions, you have so many unknowns, but you were given with a force. If you start solving everything related to the tension, because you have a pulley and you can use the equation for the pulley that you learned in chapter number 2, you can easily go from here and get the value of the tension. Then from this tension, if we go to the pulley, then we will go to the pulley B, and that way we can get that force that is needed. Just for that, and then we can worry about the members. How so? So you will get a pulley E. As you can see here, you have a tension going up and you have another tension going up. If you do sum of forces in the y direction, which is 2E minus 700, which is this one, will give you a result of the tension equals to 350 pounds. You just solve one of the issue. With that T, you can move up to C now. If you have C right now and you have your 350, it's very simple. You have 350 right here, 350 right there, and you have two reactions that are acting on the pin. So if you simply do a sum of force in the X and the Y direction, you will get those reactions, CX and CY. Will you need them? Yes, of course. Why is that? Because if you go back to this problem, you will realize that you need all the reactions acting on these pins, and those are the reactions that you need to calculate. So if you go to this one, you can see that you have two unknowns and two equations that can be established without doing any moment. So that's what it was done. Sum of forces in the X direction, sum of forces in the Y direction, you get CX and CY and CX. And then you just repeat the same thing for B. Which one is B? This one right here. You have a cable pulling like this. You have this guy too. So if we do a free body diagram with the 30 degrees and everything, we can easily solve the same problem by applying equations of equilibrium in Bx and Y, and then you get Bx and By. Why is this so important? Because at the end of the day, when you have all of your unknowns laid out into this particular bean and well, in this particular bean, you already have the information here. You have the information here. All you have to do is to find information right there. Oh, sorry. You also have another unknown, which is this. If you study the problem, you only have three unknowns: AX, AY, and TBD. Or, the tension or force. We can call it force BB. So, once you have this problem laid out, what should I do? It's always the same thing, equations of equilibrium. Because if you have three unknowns, by applying the three equations of equilibrium that you know of, then you will be able to solve the problem. But the first question is always, where do I do moment around? Do I go with moment around A, moment around B, or moment around C? When you have that question, the best answer would be, it will be the point at which I have more unknowns, because then I can get rid of those reactions and do moment. If you do moment around A, you will realize that AX and AY, they don't do any moment, and therefore you can have a single equation that will give you the result of TBD, because you already have this, you already have that, this and that. And if you solve your equations around A, you will get tension BD or force BD, if you want to call it that way. Then once you do that, you can do sum of forces in the X direction in order to find AX, and then sum of forces in the Y direction in order to find AY. Please note that every time it was supposed or it was assumed that the members were in tension. The way I always do it, I carry the negative value across all of my calculations instead of flipping the arrow. But if you want to do it that way, I'm perfectly fine with that. But remember, it has to make sense. Then the only thing that is done or that we need to do is to analyze point D, in order to get my two reactions, dx and dy. So if I have my point here and I already calculate this value, because that's what we calculated in the previous slide, then all I have to do is to apply sum of forces in the x direction and the y direction in order to get the value. So with that, you conclude the exercise. And guys, the key with this was to establish a path. How so? Before throwing any numbers, you need to look at the picture, like this. And once you look at the picture, you need to realize what would be the best path for you to follow. If you don't find the right way to do it, you could spend hours and hours just going nowhere, and that's not the strategy. You need to use your time smartly, and because of that, always go with what you know and move in a way that will make sense for you. And with that, guys, we conclude chapter number 6. We're moving very quickly, and this chapter is supposed to be easy. It's just, if we talk about chapters, so chapter 4, 5, 6, and 7, they're very close to one another. So if you understood chapter 4 and 5, 6 should be fine. But if you didn't, just shoot me an email and I can help you out. Alright, that's it for this video. Let me know if you have any questions, and if you don't, I will see you in the next one. Thank you.